Hello students, today is the first module of this spread spectrum communication course. So, we will start with the introduction of spread spectrum communications. In this module, we will try to understand what is the meaning of spread spectrum communication, what kind of communication system is it, what is the basic difference of these spread spectrum communications from the narrowband communication systems or conventional communication systems. With respect to the block diagram of a digital communication systems, we will try to understand what are the basic difference of this block level understanding. It is a basic difference of this spread spectrum block diagram from the conventional block diagram of any conventional communication systems. We will also try to understand a brief history of this spread spectrum communications, and we will also learn the key benefits of designing such kind of communication systems, and we will end up with the different types of such communication systems which are useful for the practical implementation. Okay, let us start. As the name suggests, it is a spread spectrum communication system. Please check the term spread spectrum minutely. So, we are designing a system where we are playing with the spectrum of a signal, and as the name suggests, we are spreading the spectrum of the signal. The spreading means it has a underlying part of it is we are having an additional modulation involved in the signal processing for spreading your signal, and this modulation, additional modulation, helps you to expand the signal bandwidth, and the bandwidth, this expanded bandwidth is beyond the minimum required bandwidth for the data modulation. So, for example, if I take a BPSK signal, and if its minimal required data, if it is a 1 Mbps signal, and suppose 1 Mbps is the data rate required, and we required 1 megahertz bandwidth at least to transmit this signal. Spread spectrum communication systems will require a bandwidth which will be higher than this 1 megahertz bandwidth. So, in the spread spectrum, we will transmit the same 1 Mbps signal, but with higher bandwidth. That is the meaning of spread spectrum signal itself. Lot of question immediately starts: why should we communicate with a bandwidth which is more than the required bandwidth? What are we getting some key benefits by doing this? And what are those? If yes, what are those benefits? So, let us first understand what are the benefits because of which we are intentionally spreading the signal, and some redundant bandwidth we are utilizing to transmit data, for which the data modulation bandwidth is really far below than the spread bandwidth. The spread spectrum communication system is basically very useful for certain cases. Number one, we by meaning of spreading the signal, by doing the spread spectrum signal, we can actually suppress the interference. Remember, whenever we are talking about the interference, we are talking about a narrow band interference. The bandwidth of the interference will be much less than the spread spectrum signal or the spread signal. So, it may be the bandwidth of the interference may be in the order of the actual data modulation, but it is far less compared to the spread bandwidth. We will see later that how this suppressing of interference will happen only because of spreading the signal bandwidth in the due course. It also helps us for making interception difficult. Interception means suppose you are a communicator and you are communicating with an intended receiver. So, this is the intended transmitter, receiver, and communication needs to be established between these two. And take an example of a satellite communication going on from the ground surface to the intended satellite receiver, and there is a flight going on, and which is actually the enemy flight, and he is having a communication system inside, and his task is to detect whether actually some communication is actually going on from the surface to satellite or not. So he will always try to intercept what is there in air, and whether if he understands what the frequency of your transmission is, he will try to also detect whether actually in that frequency there is some communication going on or not. If it is my enemy flight, he will also try to jam my signal. So now you see, we are talking about a communication system where we are trying to design the communication system which will be resilient of having any interception from the enemy, which will also be actually very stout and robust in the signal design in such a way such that the low probability of intercept is inbuilt in the signaling system itself and the radio design itself. So spread spectrum modulation or spread spectrum communication or moduling giving an additional modulation by spreading the spectrum of the data underlying data modulation will help you to make the interception very difficult for the enemy. How again we will see. It also helps the spreading of signal. It also helps to accommodate the fading and multipath channels. What is these two terms? I should say little bit. In a wireless communication scenario, we know that when the signal gets transmitted with one transmitting antenna to a receiving antenna, this is a free space actually. It is a space within which the electromagnetic wave will propagate between the transmitter and from the transmitter to receiver, and the path is always not a direct path through which the signal flows from the transmitter to receiver. The signal also flows via the multiple paths. It gets scattered or reflected from the different scatterers present in the environment, and it reaches like this. So like this, the multiple paths are possible. Via multiple paths the signal reaches to the receiver. This is a very common phenomena that happens in a wireless domain, and we call it a multipath propagation. And because of this multipath channel concept and the fading, which is basically the attenuation and changes in the phase, attenuation in the amplitude and change in the phase of the transmitted signal with which you receive the signal at the receiver. You receive the signal at the receiver. With that whole concept of the fading and the multipath channels, your received signal needs to be clarified, needs to be cleaned up before your detection, demodulation and detection process proceed in the receiver circuit. As spread spectrum communication helps us to mitigate the fading and the fading due to the multipath channels in the received signal a lot. It also helps us for the multiple access capability. What is this multiple access now is, suppose you are in a wireless environment and you are using a typical technology to communicate with your receiver, and then like you, there may be multiple users who are at a time trying to access the radio environment or radio channel to transmit their corresponding data to their own receivers. So it is a multiple users simultaneously trying to access the wireless channel to transmit their data. So then it is a multiple access of the same wireless channel is a very common phenomena in a wireless environment. So how will you do it? You can understand that if a lot of us trying to send our data simultaneously using the same frequency at the same time and you use the same bandwidth, so there is high possibility that the signals from me and from my neighbor will collaborate and they will overlap with each other, and they will also create interference to each other if some extra measure is not taken during the due process. and so you need to take some preventive measure to segregate the signal from the different users. The technique by means of which we can do it, there are a lot of techniques available for this multiple access and to reduce the interference from the multiple users in the when the communication is going on. And space spectrum actually gives a very nice facility, provides a very nice facility to provide this multiple access in a multi-user environment. It enables the multiple access capability because it inherently uses different codes for the transmission. It uses different codes to spread the signal of the different user data. We will see little bit some detail of this capability later on again. In the due course, we will also address the different multi-user interference handling techniques in the receiver with respect to the CDMA technology. So, these are basically the 4 different use cases for which the space spectrum communication systems are found to be useful for. There are some more also we will see in the coming slides. Now, see one thing that one may ask a question that when we are using the space spectrum signal, so suddenly the signal bandwidth has increased than the minimum required bandwidth. So, in the receiver design, so I needed a wider bandwidth filters to filter the signal. I need to filter the signal after the antenna. So, once the filter bandwidth has increased, so as if am I not actually allowing the larger noise power to my demodulator and the detector circuit later on? It may seem that we are allowing, right? But remember, if I am thinking that the signal is following a Gaussian process and a Gaussian noise is also applied on the top of it, then we understand by the fundamentals of the match filter that match filter sampled filter output will give me maximum SNR, which will be inversely proportional with the power spectral density of the noise. So, hence the output power of this filter will be the noise power at the output of this filter will be irrelevant, and hence there is no fundamental limit for us to use the space spectrum communication. So, remember, there is no fundamental barrier. There is no question at all to think that the noise power will be increased in such kind of the system and it will put a fundamental barrier in the implementation. It is really not, thanks to match filter concept. So, let us come back to revisit the key features of this space spectrum communication systems. Please remember, you may already got the idea that space spectrum communication is very useful to give you a secure communication. So, as if the communication system will be implemented only in the military purpose. It is no. The application may be in the military purpose as well as the commercial usage. Though it started with the military purpose, definitely yes, but later on it has got a very big success in the commercial network also, commercial mobile communication network. So, there are different reasons for which actually space spectrum communications became so popular. Actually, space spectrum communication gives your hide your signal below the noise floor. So, it makes you very difficult to detect whether there is a communication or there is not. So, it gives you very poor detectability. We call it the low probability of intercept. You cannot detect whether a communication is going or not. Number 2, it mitigates the performance degradation because of any inter-symbol interference that is going on, and also the narrowband interference. Already I have mentioned that when some narrowband interference will be there, we will get a gain on the top of it against that. It also rejects all the hostile jamming, and it can or unintentional interference, maybe actually interference coming from your other network who are unknowingly trying to give interference from you, and it may be actually somebody intentionally trying to send high power in your transmission frequency band and trying to jam you and disturb your communication. So it rejects the both. It rejects the intentional jamming, and it is also helpful to reject the unintentional interference. Spread spectrum, it provides the inherent message privacy. If you cannot detect what the communication is about, if your signal is buried in noise and you are unable to detect something, means your privacy of the message transmission is really very high. So spread spectrum communication is the first step, is the first means by means of which we provide security in the physical layer. Today you might have heard lot about the 5-layer security system. Spread spectrum communication is very fundamental step towards that. So it won't allow any unauthorized listener to who is not having any knowledge what kind of typical code or the key you are using for spreading your signal. They won't be able, and if he is not having any timing information of your signal, he cannot recover at all what you are transmitting if he cannot crack the key, definitely. So spectrum also provide a very coherent combining of the multiple path signals by means of a typical receiver, which we call the rake receiver, and it helps us to provide a huge gain of the received signal to noise ratio because of this successful combination of our multiple path signals. So what I mean to say here is, I showed you that in the wireless domain, you are receiving signal not only over the line of sight path, you are also receiving signal over the multiple reflected paths. These are called the multipaths. So once actually the signals are received, and these multiple paths, the signal via the multiple paths are received via the multiple delays associated to it. Once these signals are there, and you are receiving those signals, and if you can capture those signals over their corresponding delay points, and if you can successfully combine them, we call the structure as a receiver architecture. If we can do that, so definitely actually all those multipath signals will help me to increase my signal to noise power, and this capacity is there in a spread spectrum communication system, and so coherent combination of the multipath signals can enhance our SNR in a rake receiver. Spread spectrum communication can be used for ranging and precision. What is this about? So listen one thing, that suppose we understand for 1 Mbps transmission of a BPSK signal, I need suppose 1 megahertz bandwidth in a conventional narrowband communication system. In spread spectrum communication system, 10 times of this bandwidth, suppose 10 megahertz of the bandwidth we are now utilizing. So when we are using the spread spectrum bandwidth, suppose this is a BN bandwidth BSS and this is the conventional bandwidth BC. So when actually the bandwidth has increased, so you now see that in terms of the time, whenever the bandwidth is really very high, it is a wideband transmission going on, and whenever some wideband transmission goes on, actually in the time domain you can actually utilize this signal, wideband signal, for precise localization, because the time domain signal corresponding to the wide bandwidth is much less corresponding to the compared to the time duration or time signal of this BC. So now you can have a fine resolution over the time axis. You can locate the information, you can get the information over smaller time axis, over the smaller time duration. So it improves the precision of ranging. It can improve the useful information of the location and also the timing acquisition. So anything related to localization, ranging precision, timing acquisition, all those activities which are very important tasks in our commercial communication systems, they can be now performed by spread spectrum communication. Spread spectrum also allows when multiple users to sustain within a given interference with minimal interference in a zone of the geographical zone of communication, and hence it becomes actually a key factor to develop the very famous communication technology, which is the CDMA. So, we have got the very key features of this space spectrum communications in this slide, and remember one thing we have already been discussed. I hope you have got. In a space spectrum communication systems, we have, first of all, we have a data signal, and we have some key, and this key is helping us to spread the bandwidth of this data signal in such a way that we can get a lot of benefits listed here. But remember one thing, so once you are increasing the bandwidth of the signal here, the key is actually, this is a spared signal bandwidth. So, once you are using the bandwidth, increasing the bandwidth of the transmitted signal, remember that the gain of the transmitted signal is decreasing and keeping the gain bandwidth product constant in the transmission system. We will revisit this concept once I show you the block diagram of such space spectrum communication system in the next few slides. Before entering into the detail of the mathematical expression of space spectrum communication or block diagram, let us also revisit what are the major application scenarios of such design systems. Military is definitely a very important part, because we need the secured communication for military and the defense application. And as space spectrum communication gives us protection against the jamming, and it has the inherent privacy, it has low power, low probability of intercept. So, military communication system has got the maximum application for space spectrum communication. A very good example of such system is Belstar. It is also used in the global positioning system, because global position GPS is very famous for giving us the ranging precision, giving us the timing alignment over the multiple users, and it gives us immunity to the multipath also. So, GPS based timing, GPS based localization we use in our day-to-day life. Space spectrum communication is the key parameter to enable the system, enable the high ranging and high precision inside that system. Mobile satellite communication system, due to the interference rejection, multipath protection and location acquisition. So, satellite communication system also prefers the space spectrum communication. Very good examples are the Omnitrax, designed by Qualcomm, the Global Star, designed by Qualcomm and Loral. And finally comes the cellular communication, or our famous mobile communication. Due to the multiple access capability, capacity enhancement, your inter-symbol interference, this stands for inter-symbol interference mitigation property, your multipath protection, interference rejection, and your inherent message privacy, location acquisition, because of lot of the good parts that are there in the space spectrum communication. In cellular radio also, it has got a very big hit, and the example is IS-95, CDMA 2000 systems, WCDMA system, which are very famous actually in the up to the 3G communication systems in wireless. Next, let us have a very brief overview of the history, who started, where was the start point of this space spectrum communication, who did it first, and who are the legendary people who led this space spectrum communication based research, especially the finding out the different keys, designing the keys, who are the main people are and the very famous people who have done and designed all those keys for us. It was 1941 when Hedy Lamarr and George Antheil they filed a patent on the frequency hopping space spectrum communication systems, and this is the first time actually something is in pen and paper. Prior to that, even if something has happened, we are unaware of it, and we get the applications to the it was having a target with the applications to guided missiles as well. And the direct sequence signals here, they were used for ranging and tracking a radar, which we call a tracking range radar system. and it was used in the jet propulsion laboratory and it is the JPL who gave the term as pseudo noise to these direct sequence space spectrum systems from 1953. So, the first type of the systems which were actually got very big hit, one was the frequency hopping system, another was the direct sequence space spectrum systems. The earlier reported work on these PN sequence systems or the M sequences were investigated in early 1950s in the Bell Lab, and these are the group of the people Golomb and Golomb et al. Who have worked a lot over the designing of the sequences later on. And finally, actually, the earliest coherent space spectrum systems was first constructed and designed by Magnavox, and it was the code that he used inside that was the Gold code, and the code was the inventor was Dr. Robert Gold. So, the Gold codes, this code we will learn a lot, and his property we will learn a lot in one of the modules in this whole course. We will also learn what are the other codes possible are getting used in practice for space spectrum communication systems, including my M sequence also. And the first tutorial on the space spectrum communications in the literature you will find it was written by Dr. Charlie Chan, and it was published by Magnavox. So, this about the brief history to know actually who filed the first patent, where from the design of the sequences came, when the first such system was designed, and remember Bell Lab was took a pioneer role to do the research in this field. This is the block diagram level of the basic system model of space spectrum system, and we will try to just identify what are the basic difference between the conventional digital block communication system block diagram and the space spectrum system block diagram. So, we understand that it is the input data, and prior to that we have done input data that is coming, and this is channel encoding. Prior to that the source encoding and all has been done, I am guessing. This is the channel encoder which helps us to encode the data to give protection against the channel fading, wireless channel fading, and this channel we are considering here to be mostly a wireless channel. It can be any other thing also, the coaxial cable or an optical fiber cable also. In that cases the channel code encoding will be different ball game. If it is a wireless channel, we know a lot of the channel encoding techniques. For example, the convolution code, also the conventional convolution code or the LDPC code, or actually the combined coders, I mean concatenated codes where the RS and the convolution codes are combined, and so on. Remember, inside the modulator here we mean that we are having both the data modulation as well as the extra modulation that is coming because of the spreading of the signal. So, data modulation and space spectrum modulation both are actually incorporated inside this modulator. And for what you need for the spreading of the waveforms, you need a pseudo random sequence here. So, we have fed a sequence here which is helping me to spread the signal. So, basically the modulated signal here is coming in, and if it is a modulated signal, we are actually basically multiplying with each code signal, we call it a SC, and then finally the SM multiplied with the SC is the spread signal that is coming out of this modulator box. The output of the channel when it is entering into a receiver, it is entering into a demodulator block. Remember, this demodulator corresponds to the only spread spectrum demodulation process, but this demodulator needs a very high and accurate information about your timing of the signals, and tracking is also an important part that continuously needs to be going on to acquire the pseudo random sequence, to align the pseudo random sequences of the receiver to that of the transmitter. Remember one thing, we have assumed here that the receiver and transmitter are in they know, both of them know that what exactly is the key getting used for a typical transmission at that moment. So, key is already shared. and this demodulator doesn't encompass the data demodulator. After this spread spectrum demodulation, the actual data demodulation goes on, and data detection, channel decoding, data detection, everything goes on. So the basic difference that you are seeing from the conventional block is that we have a modulator, spread spectrum modulator, with along with where actually the pseudogenome sequence generator is feeding out, and this is the extra section in the transmitter, and in the receiver we have the acquisition tracking circuit board and a unit, and also the demodulation unit, an additional demodulation unit for the spread spectrum communication, additively coming apart from your additively coming on the top of your data demodulation in the conventional communication system. So these are the two blocks in the transmitter as well as correspondingly in the receiver we will be seeing in addition in this communication system. And remember that tracking acquisition, we have called acquisition means the time frequency acquisition of the codes as well as the signal as well as the carrier we need to do in the receiver. But remember, we also need to do a tracking. Tracking means you continuously, when the data communication is going on, you have to keep on track the any changes, whether any changes has happened on the phase frequency or time or not. If it is there, no, the successful demodulation won't be happening in the receiver. So the SNR gain that we are talking about from the beginning itself, it means that very nice tracking should be going on in the receiver of such system. That needs to be ensured. So there are basically three properties of that needed for a signal to be declared as a spread spectrum signal, that we have learnt already. Number one should be it's a very bandwidth very much larger compared to whatever is required minimum. It should use a spreading code, which we also sometimes call a key, and it should have a dispreading process at the receiver, which is done by correlating the receiver signal with a synchronized copy of the spreading code. Remember, it is synchronized copy. That means your tracking, your acquisition, time phase frequency acquisition is correct. It is ideally done. And let us quickly revisit the mathematical formula of such communication system. We will try to investigate how the information signal, which is having a bandwidth of B, is embedded in a larger transmitted signal which is having a bandwidth of Bs. So suppose there are the set of linearly independent signal SIT, where I can have 1 to capital M, and this independent signals S1, S2, S3, S4 to Sm, they are of bandwidth capital B and then have a time duration of capital T. So you can write this SIT in the form of Sij and phi j in terms of their basis functions, where the phi j t are the orthonormal basis functions and they have a span over n dimensional space. So I can represent any signal by means of the orthonormal basis function, and they can span over the n dimensional space. We have learned it actually in a digital communication system, if you recall, that we can write any signal that is transmitted over the space in its in terms of its orthonormal basis function over an n dimensional space. So this is the same thing. There is nothing to do with the spread spectrum yet. Next, one of the signals we transmit at over a time duration T and every time duration, and remember actually the minimum number of the basis function that you need to represent all these signals will be actually twice B into capital T. And since actually this all these signals SIT, where I belongs to 1 to capital M, they are linearly independent of each other. It also implies that this capital M should be almost equal to this 2BT. And this is to embed this signal into a higher dimensional space, with the space is suppose capital N. We need that this capital N should be very large compared to capital M. So the receiver now uses only the M branch structure, where the ith branch correlates the received signal with the known signal SIT, and receive signal with the SIT, and the receiver output the receiver outputs the signal which corresponds to the maximum correlated output definitely. So suppose we generate the signals SIT using a random sequence, so that the sequence of coefficient Sij are chosen, and they are chosen based on some random sequence generation once again, and each coefficient they are having some mean 0, and now the variance will be the total signal power Es divided by capital N, because N is the n dimensional space over which you will actually express the signal. And so now the interfering signal also can be written as 1.2 in terms of their or the same orthonormal basis function over the n dimensional space. And the total energy we are interested actually only over the duration of its of this interference, and let it is having a duration of 0 to capital T. So the energy can be easily obtained by this expression, and where the energy let us define is as Ej. So we are having the signal as well as the interference. Let us now consider that at the input of the receiver we are receiving a signal where the original signal clubbed with the interference is entering. For the sake of the analysis, let us consider that there is no noise part associated with it. And now when the ith branch is correlating this input signal with the known signal SIT, then this will be the correlated output over the duration of capital T, and we will be receiving and we will be ending up after the correlation, we will be ending up with square of the intended signal plus some part of the interfering signal. And we can show that now the obtained signal to interference ratio, because you are now ending up with the signal plus interference. So signal to interference ratio will be governed by Es by Ej into N by capital M as given in equation 1.5. Remember, this result is independent of the distribution of the interfering signals, definitely, because there is nowhere the distribution of the interfering signals are controlling the SIR. If noise is there, you have to compute the SINR. Now remember one thing, in the previous slide you please notice that as my N is much larger than M, so there is a gain involved in the signal to interference ratio in a space spectrum communication. The gain that is increased, the signal to interference ratio is increased now by a factor of capital N by M, which we have referred here as the capital G, and which we will call as a processing gain or the spreading factor. This is a very famous term that we will keep on using in the whole syllabus. Remember, this is a processing gain. So whenever you spread some signal, you end up with a gain in the signal to noise power, and we call it a processing gain, but we are losing somewhere, we are using the redundant amount of the bandwidth. Okay, at the cost of extra bandwidth you are gaining over the signal to interference ratio. Your signal power at the end of the receiver is much increased corresponding to the interference power. And in the bandwidth domain also it can be equivalently written in terms of the space spectrum bandwidth divided by the actual bandwidth required for the data modulation. To give you an idea, so usually in practical system design we keep this gain factor 10 to 1000 around. Okay, so what is the underlying meaning of this gain? So the underlying meaning of this processing gain is that now the bit error rate of any modulation scheme with respect to my EB by N naught, or suppose it is with respect to SNR, let us say, if I go ahead with that, and whatever the bit error performance we were getting, I mean suppose we are getting a 10 to the power minus 5 bit error rate at a speed or at a SNR of say 9.6 or 9.8 dB for my BPSK kind of communication systems. So now with actually the space spectrum communication, depending upon the factor G that is actually involved here, we will get the same 10 to the power minus 5 with a much higher improved SNR. So that gain, the same 10 to the power minus 5 bit error rate you will be able to get with much less value of the SNR. So that's the meaning where the gain is getting reflected on the performance of the system. So always the space spectrum communication system will give you the better performance in the physical layer compared to the any conventional communication system. But remember, all that gain is coming at the cost of your extra bandwidth involved in the system design. So question here comes like this. So we understand that when we give the convolution coding or the block coding for the channel encoding process, It also improves the performance of the whole system in the phi layer, and it gives us in the presence of noise as well as the interference, we get enhanced performance over the bit error rate. They also work by increasing the signal bandwidth. Then whether will it be fine to go ahead with block or convolution coding, channel coding, or you will go ahead with a space spectrum communication. So to choose between these two, if you ask me right now that whether we shall we go ahead with a forward error control coding, or we shall go ahead with a space spectrum communication system, who will be good, who will be bad, how to choose all that, the answer is it depends on the specifications of the system design itself and the requirements of the system, which will give you this answer. And lastly, actually we will end up with telling that what are the different kind of the space spectrum communications used in practice. We have mostly the 4 types. First one is the direct sequence space spectrum system, second one is the frequency hopping space spectrum system, third is the time hopping space spectrum system, and fourth is the hybrid combination of any 3 of these guys. And we have given a simple example. We will discuss in detail in the corresponding modules for each of them, and we will see what actually the meaning of those space spectrum communication systems mean. But here we will try to get a glimpse of what is the first one, the direct sequence space spectrum communication means. We were telling from the beginning that we have a data. The ST here, the red line, is the data that is required to be transmitted, and this data is having a duration of Ts. Okay, and this smaller green graph that you are showing going inside, this is the pseudo noise, or this is the key, or this is actually the code sequence that will actually help me to modulate my signal ST. So the SCT is the code sequence, ST is the data sequence, SCT is the code sequence. SCT is having time duration of Tc. So now see, actually we are considering, if we consider that Ts and Tc is chosen such that Ts is G times larger of Tc, then the G is the gain, which is actually given by Ts by Tc further. So once these two signals are multiplied with each other, you will be ending up with this blue signal, which is actually spread spectrum signal, which is ending up with this by multiplication of ST and SCT, where the positive part of the signal is there, you will not see any change of the phases of this SC, whereas in the negative, during the negative pulse, actually you will see a lot of changes correspondingly happening for the pulses. And finally, once this multiplication is done now between the red and this green graph and the green signals, these two signals, once they are multiplied and you are ending up with a spread signal, there is no existence of this Ts finally. You are ending up with a spread spectrum signal with the individual duration of the pulses governed by the Tc. So if I try to see this, so we have given here the expression for all those 3, and if I come back here and try to see the frequency domain, what is going on basically. So this is the spectrum of the data modulation signal, which is corresponding to ST, it is SF, and it is having a bandwidth of 1 by Ts, definitely, because Ts is the time duration of this signal. And after the multiplication, we are ending up with the spread signal, and it will be governed by 1 by Tc roughly. And so this SS is equally the convolved signal of SF into SCF. Now this is transmitted finally. So this was your SF signal, was the actual signal you started with. You end up with the spread signal, which is called SSF. You have transmitted this SSF through your transmitting antenna. So this is a wideband signal transmitted through your transmitting antenna finally. At the receiver end, you will be receiving the signal SCF into SCF, and we understand that this was my SF spectrum, and this was the bandwidth was 1 by Ts. I need to get it back. Remember, when it was traveling over the channel, there was an interfering signal called IF, who is a narrow band interfering signal, which has also entered into the receiver front end. And see the situation, the power of this interfering signal is higher than the power of the spread signal. Another important part to notice, when the signal was transmitted, when the signal was spread, the bandwidth of this SF and the power of this total SF, when the bandwidth has got increased, the power is reduced. So you are ending up here with the situation where the interfering signal clubbed with the spread signal has entered. In the receiver, we again multiply the signal, this spread signal, with their own known key, I mean the same SCT. Once we do it, by default of the signal processing itself, the spread signal actually comes back. We get back our original signal SF, which we will be filtered out by putting a low pass filter. But what is happening with this IF, where that SCT is also getting multiplied with IT. So once that multiplication happens, so now this signal is spread over a very wide bandwidth. So now if you compare the received signal power after the demodulation in the receiver, the signal power is much enhanced compared to the interfering power. So this is pictorially and with the help of a graph, this is the first level of understanding the way the space spectrum communication works, how it can reduce the effect of an interfering signals. But we will be discussing this topic in detail with corresponding to each of these space spectrum communication systems in the coming modules.